So this is the third and final week of checking in on the alum crystals, and as you can see, they're a little bit bigger. The solvent has evaporated quite a bit since last time, and the two larger crystals have sort of fused into one, and there are some smaller crystals that aren't completely dissolved in the solution on the bottom of the container. There hasn't been much change in the environmental conditions from last week. The alum is still kept on my windowsill, so it gets full sunlight as well as light from my lamp at night, and this heat and light has contributed to helping the solvent slowly evaporate. So I've started to get one larger conglomerate crystal in my vial, but what if I wanted one really huge crystal that's super high quality? Well, then you could carry out the same procedure of obtaining a saturated alum solution in the vial and covering it up with a permeable material, but then you would also need to dangle a string into the solution. This would add extra available surface area, which encourages nucleation or the start of crystal growth, and ends up favoring crystal growth over dissolution in the dynamic equilibrium. After some time passes and crystals start forming, you could pick one of the crystals to be a seed crystal hanging on the end of the string as a starting point, and either dispose of the other solid crystals or redissolve them back into the liquid solution to purify and perfect the solution. Repeating this process of perfecting the solution and allowing slow evaporation of the solvent over time will enable a large single crystal to grow. This process is slightly different to what we did in the lab, where we made the solution and simply left it alone. I ended up not with a single large perfect crystal, but rather two medium-sized crystals merging together and lots of itty-bitty ones on the outside. Both methods use slow evaporation though, and both produce solid crystals out of the solution. One important element of crystals is called d-spacing. So in a crystal, there are rows and columns of atoms arranged in what we call parallel planes. And if we look at them like this, where light passes through the crystals, we can determine this triangular relationship that helps us find the d-spacing, which is the distance between each of these parallel planes. We end up getting this equation, n, which ensures that path length is a multiple of the wavelength, times the wavelength is equal to 2 times the sine of theta times the d-spacing distance, which is d. Knowing this d value is important because it gives some insight about the spatial arrangement of atoms in a crystal. And using it in this triangle, it also lets you know what angles and lengths there are between all the atoms. This helps you better visualize the physical structure of the crystal. So using this equation and the X-ray diffraction data provided to us, we can see that it was measured at a wavelength of 0.15418 nanometers, and that the highest peak occurred at a 2 theta value of approximately 20.67 degrees, which means that theta is approximately equal to 10.33 degrees. We can assume that n equals 1 here because we had no way of indexing all the peaks of the graph, and then we can isolate d in the equation and plug in the values we do know. This eventually gives us the final answer of 0.4299 nanometers as the d-spacing distance.